Imagine a vast library with millions of books. Finding a specific book would be nearly impossible without a systematic organization system. Similarly, in database management systems, or DBMs, efficient data retrieval is paramount. This is where physical data organization comes into play. It dictates how data is physically stored and accessed on disk, impacting the overall system performance. A well-designed physical data organization scheme ensures faster data retrieval and efficient storage utilization. We will explore various concepts, from basic file structures to advanced indexing techniques, providing a comprehensive understanding of this crucial aspect of DBMs. In the realm of databases, we often talk about logical and physical data independence. While the logical structure deals with how data is perceived by users, the physical structure concerns how data is physically stored on the disk. A logical record representing a single data entity is mapped to a physical record, the unit of data transfer between main memory and disk. The mapping between these two is not always one-to-one. Multiple logical records can be grouped into a single physical record, determined by the blocking factor. The blocking factor refers to the number of logical records stored in a single block on the disk. Choosing an appropriate blocking factor is crucial for optimizing data access. A higher blocking factor reduces the number of disk I/O operations but might lead to wasted space if records are small. Pinned organization implies that records are stored at fixed positions within a block. Unpinned organization allows records to be moved within a block, reducing fragmentation but requiring additional pointers for access. One of the simplest ways to organize data is using a heap file. In this technique, records are stored in the order they are inserted, without any specific order or structure. While simple to implement, heap files suffer from poor performance for searches and updates. Imagine searching for a specific book in a library where books are placed randomly. It would require a sequential search, checking each book until you find the one you're looking for. Similarly, accessing data in a heap file often involves scanning a significant portion of the file, leading to longer processing times. Despite the drawbacks, heap files can be suitable for certain applications. For most database applications requiring efficient data retrieval, more structured file organization techniques are necessary. Welcome to Section 4, Speeding Up Searches, Single-Level Indexing. To understand indexing, imagine a textbook with a detailed index at the back. Instead of flipping through every page, you can quickly locate specific topics using the index. Similarly, in DBMS, an index is a data structure that allows you to quickly locate data based on specific search keys. A single-level index, the simplest form of indexing, creates an auxiliary structure containing pointers to the actual data records. This structure is based on a specific search key, for example, the employee ID in an employee database. Without an index, searching for a specific record would require, on average, reading 50 blocks, in the worst case, all 100. Now let's create a single-level index on the employee ID. This index might contain 10 entries, each pointing to a block containing 10 records. Searching for an employee ID involves finding the corresponding entry in the index and then reading the actual data block pointed to by the index. Moving on to Section 5, Scaling New Heights, Multi-Level Indexing. As the size of the database grows, even single-level indexing might become insufficient. Searching through a large index file itself can become time-consuming. This is where multi-level indexing comes into play. Just like adding chapters to a book with an index, multi-level indexing adds layers to the index structure. Each level of the index acts as a guide to the level below it, narrowing down the search space until the actual data record is located. A two-level index might have a top-level index with a single entry pointing to 10 second-level index blocks. Each second-level index block then points to 10 data blocks. This hierarchical structure drastically reduces the number of block accesses required for searching. Now let's delve into Section 6, the power of trees, B-trees, and B-plus trees. While multi-level indexing improves search performance, it can lead to unbalanced index structures, especially with frequent insertions and deletions. This is where tree-based indexing structures like B-trees and B-plus trees come into play. B trees are self-balancing tree structures that maintain sorted data, allowing for efficient searches, insertions, and deletions. Unlike a binary tree where each node has at most 2 children, a B tree node can have multiple children determined by its order. B+ trees, a variation of B trees, further optimize the structure for disk-based access. In B+ trees, all data pointers are stored in the leaf nodes, forming a sequential linked list. These tree-based structures are widely used in DBMs due to their efficiency in handling large data sets.